Hello, guys. Welcome to another episode together. Today we'll be talking about right-hand rule principle number 3, which is how motors work, and we'll also talk about applications of where electromagnetism is used in technology and in society. Okay, so right-hand rule number 3 is also known as the motor principle. And if you take a look on the top of course pack page 57, you'll see a bunch of these pictures over here. And I just want to decipher and explain what these pictures are all about. Okay, so you have something that first has a uniform field, and you're placing a conductor inside that uniform field. So effectively, it's the first diagram plus the second diagram equals the third diagram. All right, so let's describe what's happening right here. Okay. First off, the uniform field is one from a magnetic field source where, again, B fields go from north and they head all the way to south. That's what happens with magnetic fields. With a straight conductor, things do get rather weird because with a straight conductor, there is no actual magnetic north and no definable magnetic south. All right. North and south is all relative to where you are positioned to the conductor. So in other words, if I'm standing over here and we know that current is going up, then from the perspective over here, north is I guess from over here, and it points towards south. Okay, so if current going up, then yeah, magnetic north will be closer to me, and magnetic south will be closer to you. However, if I look on this side of that conductor, now magnetic south north is closer to you, and magnetic south is closer to me. So it does change in definition depending upon where you're standing relative to the conductor. Okay, so yeah, let's describe the one that's in the diagram over here. I think we see letter X. Yeah, so X means that the current is going into the page. All right, so in your imagination, you're putting your thumb into the piece of paper. All right, and as you place it into the piece of paper, you'll see that the current, or the B field, sorry, start to rotate clockwise. Yeah, clockwise from your perspective over there. Again, the definition of north and south changes because, for example, if you're looking at it from right over here, then north will be here and south will be here. Meanwhile, if you're looking at it on the other end of the piece of wire, then north will be up here and south will be over there. And that's what's happening in the setup over here. We're superimposing these two on top of each other. So you have a magnetic north and a magnetic south. And you know what? I'm just going to color code things just so that you can see the differences between the two. And I'll just use blue and red. All right, north, south, north, south. And maybe I'll just stick with those ones in green. That's all, just because we see that big green field there. Okay, so north and south, north and south. All right, so now let's have the pictures superimposed with each other. So I'm going to represent that straight conductor. Again, that's going into the page. So it's from your nose into the page. And from it, again, the definitions of north and south are different depending upon where you're staring at it. Because if you're staring at it on the left-hand side, it looks like that. Okay. And if you're staring on the right-hand side, then you have south over here and you have north over there. And again, you're relating this north and south with regards to these green lines here. So according to this green line here, again, north would be all the way over here and south would be here. So as a result, at this point at least, you'll see that they hate each other and they're going to move apart from each other. On the far end, let me just redraw my north from the field and south from the field. You can see that this time around, these foot poles are opposite to each other. And as they're opposite, they're going to go and attract towards each other. So as a result, this conductor will be pulled towards the right. If you need me to draw this slightly larger, sure, I can explain this one more time with a larger diagram. Okay, so here are my uniform B fields, where again, north is all the way down here and south is all the way up here. And that's true for each of these arrows. So all these arrows exhibit, south on top. It's also south over here as well, just FYI, and north over here. And it's still going to be north, at least relative to that point in space. Okay, so it's north and south is all relative depending upon where you're standing. And since the conductor is just standing right over here, it's going to generate its own magnetic fields. X means that it's going to have fields that are going to rotate like so. All right. So as a result, it's going to have a north over here and it's going to have a south over here. And hopefully you can see that the south does not like the south from the permanent magnet, and the north from the conductor does not like the north from the permanent magnetic field. All right. And on the right-hand side, the opposite happens. All right. Because on the opposite side, again, as the current's flowing downwards, we have, where is it? North on top and south, but down below. All right, so the south down below likes the north of the permanent magnet, and that's why I should draw this in a different color. That's all, just to avoid all the confusion, all this stuff over here. So that's pushing that way, that's pushing that way. This is attracted, so it's pushing this way, and that's being attracted, and that's pushing that way. Okay, so as you can see from all these perspectives over here, they're all resulting in the same consequence. This conductor wants to move towards the right. And this force, to make it want to move towards the right, this is technically known as the magnetic force, so FMAG. That's not listed in your notes, so you may want to write that down. Okay, the force on the wire is also classified as FMAG. And we got to be specific with that because in our next lesson, there's a different type of force, which is called a mechanical force. And that's why I want to be very specific with this one right now. Okay, so have that jotted in your notes. This is called a magnetic force. Now, the explanation of what's happening over here, it does take a lot of steps in getting to it. And eventually, we will get to the shortcut. But before we get to the shortcut, I really want to prove to you that all this crazy stuff, it does happen. Okay, so the first thing I'm going to demonstrate for you guys is, how in the world do we create this whole uniform magnetic field? Okay, where does a situation like this come from? Well, that's why I have a horseshoe magnet around. So let's go and see what the field lines look like in a horseshoe magnet. Switch over camera views. Place that on top. All right. And yeah, normally, oh, wait, let me just zoom it in so that everyone can see it. Where's that button? There you go. Okay, so now everyone at home can see the outcome. And yeah, I can zoom it in, bring it back into focus. There you go. All right. So I already seen that I already got copyright strikes for playing that song, so I guess I can't play it anymore. So you'll have to use your imagination for this. All right. So cue the music, and here we go. What you know about rolling in the deep. There you go. Hope you guys can see what just happened here. Right. If I move this tray out of the way, look at that. We do have parallel lines. Okay, so it is possible to create a circumstance where you have parallel B fields, and that exists with all horseshoe magnets. Remember, in a horseshoe magnet, you have magnetic north over here and magnetic south over here, and really, even though that they may be opposite ends of the pole, they find that the closest path to get to each other is directly across, and that's why you're going to see parallel B fields over here. Also, they mathematically work out that way as well. Okay, so there is such thing as making something that has parallel B fields. Next, we need to have a straight conductor that's going to pass through, and that's why on the left of it, I have this crazy setup over here, where this wire is able to freely move to the left and to the right because I can't float things here. Unfortunately, there's gravity, which will cause the wire to sink, so this crazy lever system will allow it just to float there so that it'll either be attracted to the magnet or repelled from the magnet. Okay, so that's the whole purpose of this crazy setup over here. Now, I want to simulate the same thing that's listed in your notes. So it's showing me that the B fields need to point upwards. Again, B fields go from north to south. So I need to take the setup and I need to flip it around, right? So that my B fields go from north to south. Next, in the setup over here, just to make sure that it goes in accordance to what you guys have, it shows that X means that the current is coming towards me, okay? And that means that I need to have positive coming from your side and negative coming to my side. Right, I don't know if you can see the colors, but here's the red wire, and trust me, it's connected to the red side of my power supply. All right, so my current leaving from my power supply, traveling all the way across, all the way down the wire, and then it's pointing towards me. So we have the current going towards me. We have our magnetic field. It's going to be placed just like this. And in our predictions, it says that there's going to be a magnetic force acting on the wire, causing the wire to move towards the right. Ready to see that demo, guys? And whatever with copyright infringement. Let's go play the song anyways. Ready? Cue the music. What you know about rolling down in the deep when your brain goes numb? You can call when these people seriously? Put that stuff there you go. Slow motion, yeah. In slow motion. Yeah. Of course. I tested this out earlier and it didn't work until now. And there you go. 10 out of 10. There you go. There's my musical instrument. Okay, let's just see it one more time. Oh man, that's disappointing. I wish I had an oh no track that I made myself. Again, I don't want to get any sort of a copyright scratch on it. So we'll just let this be. All right. So yeah, I tested this and it was working. And you know, that's just how it is with regards to any sort of scientific experiment. And I think many of you guys were even asking me about that already. Like, why is your whole sound experiment failing? And you can see it just, that's just how life is. All right. Things don't always work out as you would hope it to be, but that's why you persevere and you try and try again. So if it doesn't work the first time, figure out what's wrong. And then hopefully the second time around, cue the music, and there you go. All right. You can see that the wire is being pushed towards the right. That is the magnetic force, and it does happen. Yeah. Wow. It does happen. There you go. Okay. Back to the screen now, because again, this explanation over here, it's telling you the science of how it works, but that's a lot of steps. So how about we talk about how to solve this problem in less steps? And that trick is known as right-hand rule number 3. Oh, I had it all animated out. Oh, well. Yeah. What is it? Two magnetic fields interact with one another to produce a force. If the conductors that carry a current cuts through the existing magnetic field, it experiences a force perpendicular to both the conductor's charge flow and the external magnetic field. The strength of this force depends on the strength of the external magnetic field and the current going through the conductor. That is very true. All right, do you need to copy it down? No. For grade 11, you just know that this is the resulting outcome. That's all you need to know about it. There is a mathematical formula for it, and we save that for the world of grade 12. Okay, so yeah, take the time right now and jotting down right-hand rule number 3, and then we'll continue from that point there. Okay, I hope that's enough time for you to jot down what was listed over there. Okay, so this is called right-hand rule number 3, also known as the motor rule. All right, depending on textbook you read it by. And here's how the shortcut works. First off, use your thumb to describe the direction of current flow. So in this setup over here, again, the current is moving away from the camera and towards me. And that's why the thumb is pointing this way. Next, your lovely fingers over here, you need to orient from magnetic north to magnetic south. Remember, your fingers point towards the South Pole. So that's why I have it all set up like this. All right, so as long as the current is going towards me right now, and as long as the B fields are going upwards, you'll see my hand is the direction of the push. All right, so that's why the wire got pushed towards the right. Now, other teachers, they'll show it a different way, and they'll hold it this way, and that's perfectly fine as well. All right, so if you want to hold it this way, by all means, okay? The thumb is direction of current flow. Your finger points into the magnetic field lines, and then your finger that's tilted at 90 degrees, like so, this is telling you the third resulting force. All right, and the force in this case over here is pointing this way, where from your frame of reference, at least, it's moving towards the right. Okay, so that's right-hand rule number 3. If you're a half-decent artist, maybe you want to draw that diagram on the right-hand side. And if you already print out the course pack, then you just label on top of this diagram here. All right, that, again, your thumb points in the direction of current flow, so you'll list it with the letter I. Now, technically, current is a scalar vector, but I think in your textbook, it just calls it I with an arrow on top, just to tell you that even though current's a scalar quantity, we're still giving it a direction in the setup over here. Okay? Oh, you missed out on so much fun, didn't you? You can find it in the recording afterwards, as well as the mistake I made. All right, it's okay. You just missed out on me just proving that this is true, but we'll just go through all the theory right now. Okay, so the current is pointing, again, towards wherever your thumb is pointing. All right, your fingers always point from magnetic north to magnetic south. So north is on this side and south is on the far end. Lastly, your palm points in the direction of the magnetic force. So the resulting force, in this case over here, gets pushed upwards. There you go. All right. So these problems over here, they're always going to be three-dimensional, and that's the reality. That's why your hands are always held in this weird, funky fashion. Okay. So let's go through some examples, just proving that, yes, when you have a conductor with current flowing through it, and you have a permanent magnet around, it will cause the conductor to bend. All right. And I will demonstrate that again. No big deal. Oh, copyright infringement. I can't play that video. It's on Spirit Fingers. What exactly are they? If you ever watched the movie Bring It On, you'll know what I'm talking about. Your good old Spirit Fingers. Okay, so let's go through these examples over here. Again, if you're wondering how do you draw this down if you didn't have a printer available, well, you just draw this big fat C over here, and then on top, S down below, and then that circle represents the conductor. And the X tells you that the current of that conductor is going into the page. Always good to have a straight conductor lying around. Here's mine. Okay. Okay. So again, this C shape over here represents a permanent magnet like this guy over here. All right. So magnetic north is on top, magnetic south is down below, and again, the B fields always go from north pole to south pole in this fashion. All right. So the B fields always go from north to south. Okay. Hope I labeled it properly there. I think I did. All right. Where north is here and south is over here. Okay. All right. Now, the question is, which way will this conductor move, at least in this setup over here? So go ahead, take your hands out and follow along. Now, my screen's on the opposite side, so you're going to see the mirror image of everything I'm doing, okay? But yeah, we have the B fields going from north to south, so that's what you're pointing towards. And then the current is going into the page, so you're pointing right into the screen, right? I'm pointing to my screen on the other side. So at least from my perspective, it looks like the wire this time around is going to push towards the left, okay? And I think that's what you'll see as well. So let's prove this to show you that, yeah, this stuff does happen, all right? And I hope that it'll work properly this time. In fact, what I'll do is I'll take the magnet away, and then I'll see if this heats up when I just turn it on as is. Yeah, I see some sparky sparks over there, so this will work at least in this setup here. We still have a setup where the current is starting from the camera's perspective and flowing this way, okay? Again, we're assuming conventional current flow, even though it's not correct according to the scientists in the last 100 years. We're going to follow along with what was deemed as correct in the past 300 years. Okay, so we're going to assume current flow. Current goes from positive to negative. That's why we're using a right-hand rule. So the current is coming this way. Our B fields are going from north to south, and as a result, the conductor should push this way. All right, so I'm going to take my conductor. I'm going to place it like this to match it up with the picture. No, wait, you guys will see it like, how will you guys see it? Oh, no, I just want to show it the same way you guys will see it. I think you guys will see it like that. All right. So what you'll notice is that once I turn on the current over here, the wire will get sucked into the permanent magnet. So shall I cue the music again? The original audio track? There you go. Here's an original recording just by me. And hopefully it plays properly this time. What you know about rolling down in the deep when your brain goes numb? You can call that mental freeze. When these people talk too much, put that stuff in slow motion, yeah. In slow motion, yeah. There you go, all right. Science does work out. It does, all right. So in your notes, what you would state is that in this case over here, you'll have an arrow pointing this way, and that describes the magnetic force. The magnetic force will be pointing towards the left. Okay, let's try out the next example. Now, this is all at a weird angle because that's how it's typed out in the textbook. If you want to make it all level like so, you're more than welcome to in your notes. Okay. Okay, so in the second example, there is one piece of mystery, and it is which side is north and which side is south. Is north on top or is north down below? We have no idea right now. But they're giving us other clues. In fact, with these problems over here, you need to have at least 2 clues to solve for the answer. All right. And what this question is telling you right now, or the statement, is that initially we have a dot over here that tells you that the current is coming out of the page. Okay, so make sure your thumb points towards your nose. Number 2, it tells you that the magnetic force is pointing towards the right. So that's F magnetic. All right. When it comes to test time for these things, at least in the classroom, I always love this part here, because all I see are students that just do this, right? They touch in their nose, they touch on a piece of paper, and they just move their hands around or whack things in the air, trying to figure it out. So it's quite amusing, all right? And I want you guys to do that at home right now as well. You see that there's a dot. So that dot means that your thumb needs to point to your nose. But you also have a magnetic force, and that magnetic force is pointing towards the right. So go ahead, orient your hand where the magnetic force points towards the right. How are you holding your hands? Like this, like this, like this, like this. Are you using the wrong hand? Okay, remember, use your right hand for this. Okay, so I'm looking at the screen right now. Thumb is pointing towards my nose. Magnetic field is pointing towards the right. So I have to hold my hand like this. So yeah, you're gonna look rather silly like this. But this is the only way for it to move in this direction, meaning that magnetic north needs to be on top and magnetic south needs to be down below. All right, so that would be our answer. North is on top, south is down below. Just checking my answers again. Yep, there you go. All right, third one. Again, this is just the horseshoe magnet oriented in yet another direction. And I can't tell if that's an X or a dot. I need to refer back to the course pack. What is there? Is that a dot? Looks like a dot to me. Okay, so there's a little dot there. Now that dot is telling us that the current, what color am I going to use current? I'll just stick with red, why not? Okay, that the current is flowing this way. So that's the direction of current. It's coming from the back and moving towards the front. Okay. You see an X on your page? I can't tell right now. My eyesight is that bad. We'll just pick one and go with the flow. Yeah, if you call it an X, then we'll call it an X. That means that the current is going the opposite way. That's okay. Okay, so the current is going into the page. That's perfectly fine. In fact, this is easier on the hand, okay? Because you have current going into the page and your fingers pointing from north to south. All right, your fingers always point to magnetic south, and your hand is pushing into the horseshoe. So the resulting magnetic force goes into the horseshoe. There's your FMAG. Okay, so when you answer these questions on the test, make sure you label on top of the diagram and you tell the reader that this is the resulting magnetic force. It's moving into the page. So once again, in the first example, the magnetic force is moving towards the left. The second example, the magnetic force, MAG, wasn't listed there, is pointing to the bottom right. And in the third case, the magnetic force is pointing to the right. Okay, so no, there's no way you can memorize it any other way other than using right-hand rule number 3. Okay, yes, question?
Sorry, I'm confused. Do you mind going over the third one again?
Okay, the third one, because the students are saying there's an X, I can't see from here because my screen is really far away. And my eyesight's going down the drain as well. All right, with that X over there, what that's telling you is that the current is going into the page. That's why I is pointing in, okay? And yeah, I'll stick with red for current. Why not? I know I'm not very consistent with these color codes here, okay? But current is going into the page, all right? With the current going into the page and north being down below, we know that we need to point our fingers upwards because this is the direction of our magnetic fields, okay? Magnetic fields always go from north to south. So current's going into the page. B fields are going from north to south. So your hands is being held up like this. At least from your perspective, it'll be held up like this. So as a result, you're pushing your hand towards the right or into the horseshoe magnet. So the resulting magnetic force goes into the horseshoe magnet.
Oh, okay, I get it now. Thank you.
There you go. All right. Yeah. And just to show you guys that, yeah, that this is the outcome, my setup is still that of the first case, all right? And the only difference between the first case and the second case, other than the fact that it's tilted, is that I flipped the current around. So let me go and do that, all right? I'm gonna take this conductor over here, I'm gonna move it all the way to the front, and I'm gonna take the red conductor and drag it all the way to the back. Okay, so in this case over here, we have current that's starting from my side, moving towards the camera. Just like in the second example with the dot. Okay, so it's coming straight towards you. We still have north pointing up above and south pointing straight below. So in the setup over here, it should be one such that the conductor hates the magnet and will try to race away from it. Okay? So again, this is the second example. Let's see if it really works. 3, 2, 1. And there you go. It hates it and it's pushing it away. And as you can see, it matches up with our hypothesis over there. So that's the whole purpose of right-hand rule number 3. All right, it's to relate what would theoretically happen with what does happen whenever you have a permanent magnet and a straight conductor. How will we know which rule to use? Through practice, you'll know which one is which. All right, just as a reminder, rule number 1 is that of a straight conductor. All right, so you have current going through a straight conductor, and all you're curious about are where are the B fields around this. Okay, so if my current's going up, my B fields circle this way. And if my current's going the other way around, my B fields circle the opposite way. Please don't say clockwise or counterclockwise, because your version of, your version of clockwise is my counterclockwise. So that's why I don't want you guys to state that on a test. Instead, just draw the arrows or the chevrons indicating the direction of the B fields. Or I can tell you the direction of the B fields and just tell me if it's an X or a dot for the direction of the currents. That's right-hand rule number 1. Right-hand rule number 2 is with regards to any sort of solenoid. So you take a straight piece of wire and you coil it up. The moment you coil it up, you'll have one end of the solenoid which will behave as magnetic north, like in a permanent magnet, and the other side behave as magnetic south. And the question is, which side is magnetic north? Which way does the direction of the current have to flow? Okay, does it have to exit on this end, or does it have to enter in from this end to make north face the way it does? That's right-hand rule number 2. And right-hand rule number 3 is the motor principle, which is this one over here. Okay, where it's a 3-dimensional problem. That's why you either hold your hand like this or just prepare to slap a piece of wire. Like in the setup over here, we have current moving towards you. B fields go from north to south, and that's why the wire got slapped towards the right. Okay, so that's the reminder of all the 3 rules one more time. Okay, so would you look at the diagram? Yeah, you have to look at the problem. All right, so the problem will be specific of one of the 3. Okay, so infer from the diagram which rule am I looking for and what I'm trying to seek at the end. Any other questions? Okay, again, rule number 1 has to do with regards to a straight conductor. It's also known as Oersted's principle. Anytime you have a straight conductor, it's going to create B fields that form concentric circles around it. And the question is, which direction are the concentric circles oriented? Okay, clockwise or counterclockwise, but you'll just draw it as those little arrows, also known as chevrons. Okay, so this is the motor principle, and the motor principle, again, is a 3-dimensional problem with a straight conductor, but you've probably also heard of something called a motor. All right, and a motor operates slightly differently. In fact, before I move on, one of the questions from the homework, I just want to revisit this one from a different perspective. Okay, the first time around we answered this question from 2 days ago, we answered this from the perspective of right-hand rule number 1. Okay, so let's solve the same problem using right-hand rule number 3. And to solve this using right-hand rule number 3, what you want to do is that you want one of these conductors to be mobile and able to move, and the second one just to be a fixed object, creating its own magnetic field. So in this animation over here, I have X as the fixed conductor. So in other words, I took that conductor over here and I glue gunned it on top of the table, so it's not able to move. But I still pass current through it, meaning that it's going to create its own magnetic fields. And the question is, how does this magnetic field interact with the second conductor that's parallel with it? Okay, so from our homework from that day, in the setup over here, we noticed that the 2 conductors will separate from each other. Right, that was an outcome from our homework. Let's prove it again using right-hand rule number 3. So with that X, we know that the chevrons are all going to rotate in this fashion here. Okay, which, yeah, from your perspective is clockwise. All right, but what we're really paying attention to is what's happening with these B fields as they interact with this straight conductor. Because as you know, through the straight conductor on the right-hand side, the B fields are all pointing downwards. So your hands will all be pointing down. The dot tells you that your thumb must point towards your nose. Okay, and as a result, the force acting on that conductor will be pushing it towards the right. So that's what's going to happen here. The magnetic force will cause that red conductor to move towards the right. Now let's unfreeze the blue and freeze the red. Okay, so the blue will be the mobile conductor, and the red one will be the fixed one. Now, with the fixed conductor, this red one over here, I'm not going to draw all the circles for it, but you know that red means, according to right-hand rule number 1, that the thumb points to your nose, and the B fields are at least traveling downwards relative to where the blue conductor is. Okay, so the blue conductor sees nothing more than they're not perfectly parallel, but at least from this perspective, it looks like relatively parallel B fields. So go ahead, orient your hands, top to bottom, okay, because B fields always point from north to south. X means that your thumb must point into the page, and as a result, the conductor will move towards the left. Okay, so this conductor will move towards the left. So this is a different way of proving to you the same outcome. All right, so you could prove the outcome of your homework from 2 nights ago either using right-hand rule number 1 or even using right-hand rule number 3. In fact, I do want to emphasize something to you right now, which is another setup of this. So right now I have just, one straight conductor. If I turn it on right now, as you saw, nothing happened because it's not interacting with any other B fields. But if I had another setup like this, okay, and that's why I built a second one, and I hang this on top of, or not on top, right beside the first one, like so. Oh. Oh no, what happened? Okay. And I guess the challenge now is calibrating this thing. So just forgive me as I take a bit of time trying to bend this back into place. That's what you get when you make homemade objects. They don't always maintain their shape, and they bend out of shape. Yeah, and one of the realities is that lab demo equipment, it's brutally expensive. All right, if you try to buy one of these things for high school purposes, oh, can you imagine how much they charge here? That's right. You can go buy a Wii for one of these things. That's how much they charge. It's ridiculous. All right. How much did mine cost? Well, I looked for some scrap metal or some scrap copper lying around in my parents' house. Adopted it for this, same as some scrap wood. So this is effectively free. There you go. Okay, so let's see if this free one works. And I guess that's one of the problems about free. It may not work all the time. Okay, so I want to set it up exactly like this. All right. Now, I've already built this in such a way that there's going to be a short circuit on that side. All right. So there's a conductor that goes up and all the way around from your perspective. So I need to complete the circuit over here. One way I can test to make sure the circuit is complete is the spark test. Because again, I'm passing a lot of current to make this magic happen. So if it doesn't spark, I know that there's something wrong with the circuit. And there is. I don't know where. Okay. I think the best way to ensure that's going to work is if I clip it over here. And come on. Really? Is this wire fried? There's no way it's fried. Okay, so it is lighting up. Yeah. Okay, that works. I don't see sparks on this side. Yeah, if you're wondering, is this high voltage? No, I'm just using 6 volts right now, but I am passing probably around 10 amperes of current. Yeah. And yeah, if it fails, it fails. So, oh well. So that works. Okay, it doesn't work. That's okay. We're live right now. I don't want to spend too much time on this. But as an outcome, in the setup over here, it'll be the same as that. All right. So what you'll witness is that these two will spread apart like so. Okay. So that's what the demonstration should have demonstrated. And oh well, so much for free. I tried. I don't know. Maybe I'll try at the end of the video just to prove to you that it still works. I just want to cut to the chase right now. Okay. I also wanted to emphasize another thing is that, this setup over here, I know it's going to be challenging because one of the things that I've done this demonstration so many times, if you look closely up here, I know the air perspective, you can't see it. Most of this, the insulation has melted away because of all the sparks and the high current that's been going through this thing. Okay, so now it's all charred up. I technically have to sand it all down to make sure that it works brand new every time, and I don't do that. All right. So yeah, if everything was working, then this would spread apart, and it will spread apart by a known amount. In fact, if I double the current, it'll spread out even further, and if half the current, it'll drop. All right, and it's going to drop relative to a known angle. All right. So in other words, in the setup over here, I can actually determine, what the outcome of is of 1 ampere in the setup, what the outcome is of 2 amperes, and what the outcome is of 3 amperes, and so on and so forth. In other words, I made a very crude but a fundamental testing device over here. And that's one of the rules with regards to fundamental units. All right. Now, I did mention earlier that with regards to current, current is a fundamental unit, even though current can be described in coulombs per second. And the reason why current is a fundamental unit is because a coulomb, as you may know, is 6.28 times 10 to the 18. So that's 6 followed by 18 zeros. If you imagine that as as marbles, that's a lot of marbles to count in one measly second to describe 1 ampere of current. All right, and for most kitchen appliances, they draw at least 10 amperes. All right, so that's a lot of electrons flowing through, and there is no instrument right now that can currently count that quickly. That's a ridiculously huge number, 6 followed by 18 zeros. All right, no machine can count it. What we can count is the setup over here. So in other words, depending upon the amount of current that's being put into the system over here, it'll split apart by a certain degree. And if we double the current, it's going to increase by yet another degree. So because this experiment can be redone time and time again, that's why ampere is a fundamental unit. There's a diagram over there, and yeah, it's supposed to work out. Oh well, it didn't. Okay, so yeah, by the force of their magnetic separation, you can define the definition of 1 ampere. So there's the definition there. You don't need to copy it down, but there it is. Okay, the SI definition of 1 ampere is the current required to force these two conductors, if they're 1 meter long, to separate them by 2 times 10 to the negative 7 newtons for every meter of wire. Okay, and as I said, the reason why an ampere is a fundamental unit is because a coulomb can't be counted. So we can't count in coulombs, but we can measure in amperes because we can create a standard. Right, meters, we can determine meters now, be it by the speed of light and by time. All right, how do we accurately determine time? By looking at a cesium isotope number 133 atom. All right, when you give it a little flick on its outer electron orbital, the electrons start to resonate. And as long as you keep on swinging it back and forth, kind of like a swing set, it'll have a natural tendency to want to pendulate like this. All right, and that's what happens with the valence electrons of the cesium-133. They pendulate, and after a few billion pendulations, you could look at the number online. That's the definition of 1 second. Okay, and that's what we want to do right now. We want to create numerical standards where you can recreate that measurement again, even if the original one breaks apart like that, like this one here. Now you know. Okay, moving on to our next topic, which is on the world of DC motors, okay, which is slightly different than the motor principle. The motor principle, again, is with a straight conductor and a horseshoe magnet. A DC motor is a toy motor that you're probably familiar with if you ever played with race cars before, okay. There's a tiny little thing casted in, well, shielded in a piece of metal with an axle in the center, and as long as you apply voltage through it, the axle starts spinning. So let's talk about the science of it. And one thing to point out is that with regards to motors, they follow right-hand rule number 2. So watch out, right? So people think you need to apply right-hand rule number 3 for this, but no, as you can see in the center of all motors, it contains a solenoid. Okay, that's the driving principle of all motors. So this is a simplified diagram of a motor, but it'll get the idea across, all right? In the center of the motor, there is a solenoid, and the solenoid is attached to an axle. Now that axle, the solenoid, and these brushings over here, that's known as the armature. Okay, so the armature contains the axle, the solenoid, and the commutator. What exactly is a commutator? Well, it's just these semicircles that over here that temporarily make contact with one of the brushings. So in this diagram over here, you can see that, for example, on the positive end, here's the positive conductor. It goes to the brush on the back, and this semicircle over here makes electrical contact with it to allow the current to make it through the center of the motor, and they all flow downwards through the center. And you can see when you trace it, it returns back through here. It makes contact with the second commutator, which is only half commutator, makes some contact with the second brushing, and finds its way back to the source. So you do have a complete circuit. So that's why you need to have the commutator and brush. It's the only way to deliver the electricity from the outside world to this middle piece that freely spins around. Okay, now there's a difference between a DC motor and an AC motor. The picture that we have over here, which is the same as in your course pack, so if you've already printed it out, we're talking about the top of course pack page 57. Okay, the picture's on the top right-hand side. So you don't need to copy it down, but know that that's what it looks like, at least three-dimensionally. Okay. All right, so again, this video is recorded. So if you haven't printed out page 57 yet, then you can print it out afterwards or copy it by hand afterwards on your own. And then you can just rewatch this video again so you can follow along. Okay, so I'm just gonna run at my normal pace, assuming that you've already have this printed out. Okay, all right, so we know that this is a DC motor because when you look at these rings over here, they're split in half. All DC motors require a split ring commutator, and we'll see why when I go through the animation. On the other hand, with an AC motor does not have a split ring. Instead, what it has is that it has a solid ring over here, okay, at least in this dimension. Then it has a secondary one slightly higher up above. The one down below is connected to one end of the solenoid, and the one slightly up above is connected to the other part. They also have their own independent brushings. So you have the upstairs brushing, and you also have the downstairs brushing. And the brushing is connected to its own corresponding power supply. Usually it's an AC power supply, so that the motor is able to freely spin. Okay, otherwise it's only going to rotate 180 degrees, and then it won't spin anymore. Again, you'll see why that happens once we start talking about what's going on here. Okay, so that's how you can differentiate between a DC motor and an AC motor. DC motor, you always see that the middle part always is split in half in crescent shape. That's a DC motor. An AC motor, you will have two circles. You have a circle down below, and you'll have another circle or a ring up above. Now, for a flat two-dimensional picture, if you look in your homework, for example, this example right here, right, you'll see that the only way that you can describe two separate rings, at least on a flat piece of paper, is to make one ring bigger and one ring smaller. Right? That way they're able to dimensionalize between the upper ring and the lower ring. Okay, so that's why it's drawn that way, one bigger and one smaller, because how else are you going to draw two that are exactly the same size that obscure each other? Okay, so that's how they get away with it, at least in the notation there. All right, so to better understand what's happening over here, let's go through an animation together. Okay, I don't think you need to see my face for this, so I'm just going to cast the screen. So in case if you need to see the animation a lot smoother, then by all means, zoom into my face, and then you'll see it rotate a lot more naturally. All right, because I know it does get rather choppy in Google Meet. Okay, so again, this is a bird's eye view. The axle is right over here. Okay, so the axle goes right into the page. So the armature is able to freely either rotate either clockwise or it can rotate counterclockwise. Okay, so it can either rotate like this or it can rotate the other way around. The direction that it rotates is heavily based upon the setup. Okay, so let's see the setup of this thing here. I'm going to trace it piece by piece. Now, this is case 0. So this is not part of your course pack, all right? And the question is, what happens in this exact setup? And this is a problematic setup. Remember that current, as we're defining it, current leaves from the positive. So it leaves from the positive end, traces itself all the way across, travels down the first brush. But after the first brush, well, you know that current likes to travel through the path of least resistance. So it's just going to simply jump through both slip ring commutators, or split ring, sorry, both split ring commutators, and find the shortest path, which is to the second brushing, and find its way back. So in this setup over here, all you're going to see are just a bunch of sparks, and that's it. Okay, so it's the worst setup of it all. And that's why most motors aren't built this way, but we always use this motor because it demonstrates how motors work from a high school perspective. Okay, so in real life, we don't build it this way because the short circuit is a waste of electricity, and the sparks usually create a lot of carbon soot, which just ruins the setup. Okay, so normally when we analyze this, it's not through this path of least resistance. Instead, we take the armature and we slightly rotate it. Now we can either rotate it clockwise or we can rotate it slightly counterclockwise. Because what we want to do is that we just want to pair them off. In other words, each brushing has its own split ring. So since this animation has already been pre-animated clockwise, that's why I'm rotating it this way. And in this setup over here, you can see that I color-coded it. All right, the gray split ring is connected to the gray brushing, and the blue split ring is connected with the blue brushing. Now there's a proper circuit path, and let's trace through this path. Again, current leaves from the positive end of the battery. As a reminder, the positive end of the battery always has the longer lead. That's what makes it positive, and the shorter lead is always negative. So when it comes to test time, I may not indicate this plus sign for you, and you have to infer that. Okay, and again, current leaves from the positive. So it travels all the way across from the top of this diagram through the first brushing, and because it's connected to the gray split ring, that's why it's going to travel through there. It sees that there's a viable circuit path through the conductor that goes downwards, up through the back, down through the front, up through the back, down through the front, and then there's this expressway which brings it to the other side of the armature, where it goes up through the back, down through the front, up through the back, down through the front, up through the back, down through the front again. It makes physical contact with the blue split ring, which is also in electrical contact with the blue brushing, so it travels downwards and returns all the way home. All right, so this is a successful electrical path that now we can use right-hand rule number 2. Again, this is panel A, okay, on the top left-hand side of course pack page 57. All right, now that we have all the current labeled out, next thing we need to do is predict the magnetic field that's generated by this armature here. Okay, so again, use right-hand rule number 2, where your hands point in the direction of the current, and then your thumb points to the direction of magnetic north. So in this setup over here, again, place your hands so that your fingers are pointing downwards like so. Okay, have your right hand rule, or you start with your right hand, and you'll see that your thumb points to the right-hand side. And the right-hand side is always, good job, North Pole. Okay, so this end of the armature is magnetic north. Unfortunately, with the animation, when it starts to animate, it's not going to animate all my arrows here. Okay, so I'm going to erase all the arrows, and I'm just going to point out that, yes, this is still magnetic north over here, and this side is magnetic south. Okay, so as a reminder, this side is south, and this side is north. Now, we know that south does not like south, right? They don't like each other. So they're going to try to mechanically separate from each other. Or magnetically, sorry, not mechanically. They're trying to magnetically separate from each other. Now, the permanent magnet on the left-hand side, that south, will stay there. It can't move. So only the armature is able to move. So you can already predict at this point over here, it's going to start to rotate clockwise. Now, remember that over here, this is a north, and I just want to further emphasize that because these two hate each other, they're going to push away as well. Okay. Again, the north on the magnet is a permanent magnet and stationary, so it's not going to move. So as a result, the armature will start to rotate like so. I'm going to rewind back because I want you to pay attention to the animation. Look at the contact that it makes right up here. I'm going to rewind one more time. Look at the contact it makes down here. While it's rotating, does it ever lose contact with its own corresponding split ring? Yes, no, no, they don't. Okay, they stick to their own space, and that's perfectly fine. All right, and what this will tell us, all right, just as a future prediction, is that that north really just ran all the way over here, so this will still be north. Okay, so I'm going to erase everything, and we know that north is now over here. This is pane number 2. Okay, take a look on, I'll call it B, why not? This is pane B. So the first one is pane A, this one's pane B on the top right-hand side of page 57. Okay, and we're just going to predict and anticipate that this will be north over here. But we'll follow all the proper methodology. Current leaves from the positive, travels upwards through this conductor, travels all the way across, finally passes through the first brushing, which makes contact with the gray split ring. It sees that there's a viable path through it in this order, so that's why it's going to take a U-turn and travel upwards. Down through the back, up through the front, down through the back, up through the front, and then diagonally downwards. Down through the back, up through the front, down through the back, up through the front, down through the back, up to the front, where again, it's going to make an electrical contact using this U-turn over here. That's why it's going to go through the blue split ring, go through the blue brushing, and find its way back to the source. Happy coulombs of charge. Okay, now we're going to pull out right-hand rule number 2 one more time. And this time around, you see that your fingers are pointing upwards like this, and your thumb is pointing towards the left, thus proving that, yes, it was magnetic north. That did not change. So that's all I'm proving right now. I'm proving that when it rotated, probably around 160 degrees, that the magnetic poles did not change. But what is the power doing there? Well, you need to have power in order for this thing to spin. Without the electricity, as you know, the motor will never spin. So we need to have some form of EMF, some form of electromotive force. Okay, so looking at the scenario over here, well, now the tables have turned, right? North actually likes south. And we know that over here, this is south, and south does like north. So what this is going to do is that it's going to force them to want to continue to rotate. In fact, they're going to naturally rotate beyond the short circuit. All right. If you ever played with a top before or a dreidel, the moment you spin it, it'll just naturally want to spin, and that has to do with its moment of inertia. All right. In other words, as long as something has mass and you start rotating it, it just wants to rotate on its axis naturally. So it's going to rotate beyond the short circuit. Yes, you'll see a spark over here, but that's okay. That's just temporary because the momentum of its turn will cause it to keep on rotating. Let's just rewind back. Okay, we're up to this point over here. Remember, it's rotating through the short circuit. But during the rotation through the short circuit, take a look at what happens between the relationship between the brushing and the commutator. Remember, this is the before. Gray with gray and blue with blue. Let's take a look at the after. Did you guys see that? There's a changing of the guards. All right. Now the blue split ring has a relationship with the gray brushing. So this is pane C. This is on the bottom left-hand side of course pack page 57. All right, now let's electrically trace through this yet again and see what the outcome is. And you can also see as a result of this, the importance of having a split ring commutator for a DC motor. Once again, current leaves from the positive end, travels all the way across, travels down through the first brushing, which is the gray brushing, but now you can see that the gray brushing is connected with the blue split ring. It realizes that this is the only way for current to flow, so it'll just take that path. So it'll travel downwards diagonally like this, diagonally downwards again, up through the back. It'll take that shortcut all the way across and still move downwards even on the right-hand side of the armature. Again, the only path for it to complete the circuit now is through the gray split ring, through the blue brushing, and back to the source again. So here is the completed electrical path. However, this time round, you'll notice that the north and south are completely different on the armature. Remember to place your fingers in the direction of current, and your thumb will point towards, oh, I gotta draw it. I had to put my hand on the screen just to see it. Okay, so your thumb now will be pointing towards the right-hand side. So this becomes north. Did you guys see what happened? Before, it was south over here. But after the changing of the guards, it suddenly became north. And it needed to do that because if it still remains south, it will just stay stuck in this position. It'll never want to move again. Okay, so the moment it rotated like this, the bottom right-hand side behaves as north, the top left-hand side behaves as magnetic south, and they hate each other, and they push away from each other again, continuing the rotation. Okay. So it'll just, this pattern will just keep on going from A, B, C, D, A, B, C, D. So let's go through pane D now, because I haven't finished off the entire setup yet. Okay, so this is pane D. Remember that we had north over here, and north has continued its way over here. Let's rewind back. Okay, you can see that, again, there's a changing of the guards. There's the gray brushing, sorry, the gray split ring and the blue brushing. All right, they're electrically connected to each other. And as I rotate, they still make that contact with each other. So yes, logically over here, this is still north. We're still going to prove it manually, all right, because this is our last pane to practice on. So this is pane D. I know there's a lot of questions right now. Again, just follow along with the narrative, okay, and then you can rewind back and watch it afterwards. All right, so the current is leaving from the top over here, and it travels all the way across, down through the gray brushing, still through the blue split ring commutator, and it finds an electrical path of a U-turn that has to travel upwards, upwards, upwards. Take a shortcut all the way down, upwards on the bottom right-hand side, and then it'll take a U-turn to make a proper electrical contact to finish off and find its way back home. Again, when you use right-hand rule number 2, which again, right-hand rule number 2 is when you have all your fingers pointing in the direction of the current and your thumb pointing towards magnetic north, this proves yet again that yes, this side over here will be north. That will be a north pole, and logically the far end will be magnetic south. Okay, so we're constantly using right-hand rule number 2 in proving this stuff over here. Right, so in this setup over here, north likes south, south likes north. So it continues to rotate clockwise, and we let the moment of inertia cause it to rotate beyond the short circuit. And yes, you're just going to keep on repeating from panels A to B to C to D and all the way back to A again over and over and over. Of course, if you don't build it properly, it might break apart. And that's what happens with some of the students when they build their own motor. I do have an activity for you guys to do the motor, to build your very own motor. You can find the instructions in Google Classroom. However, the only way to build your own motor at home is if you have magnet wire. All right, so if you don't have magnet wire at home, then you won't be able to try out that activity at home. All right, some questions about this. Do you have your finger towards the screen? No, remember the fingers are always pointing in the direction of the arrows. So for example, in this case over here, let me just quickly trace it out. The arrows are all pointing downwards. So my fingers are all pointing downwards. And the only way for my fingers to point downwards as I hold onto it is if my thumb points to the bottom right. All right, remember, we're using our right hand rule.
So it's based off of, because like if you hold your hand a different way, then it could still technically be, like, okay, if you were to turn your hand around, then it would point the other way, but it was.
Oh yeah, your hand would point the other way around, but look, your hand does not match up with the arrows now of the current.
Okay, let me turn on my camera real quick. Okay, so this is what it is right now, what you see. What if you were to take it and do that?
Exactly, but that means that if you look at your fingers, they're now pointing upwards.
Oh wait, so they have to be pointing upwards?
They have to be pointing towards your point of view. All right. So yes, even though the arrows are pointing downwards from this frame over here, the arrows are pointing upwards behind this. Of course, if I try drawing upwards from behind, now we have a confusing diagram, and that's why we don't draw them both.
Well, no, that's not what I'm saying. I'm saying, like, do you keep your, like, in photos like this, or is it your palm or the back of your palm that is towards us?
Okay, this is your fingernails. Here is your hand. Here's your thumbnail. This is the right hand, not left hand. You know that you're being recorded right now, right?
Yeah.
Okay, just letting you know. Okay, any other questions, guys? Okay, so it's always right hand rule number 2, and just practice away at it, okay? So if you need to rewind back to the first slide and watch through it, please do so. Okay, again, I want to keep these videos at a decent length, so that's why I don't want to be repeating it over and over again here. You can watch it in the video. I don't mind repeating it after the recording's done. Okay, so let's just finish this off, and then if you have any additional questions, I can answer it afterwards. Okay, because the last part of today's lesson is on applications of electromagnetism. And yet, speakers also behave or rely upon electromagnetism. In a speaker, you have a cone, and the cone has to freely be able to move air forwards and backwards, right? Creating your waves of compressions and your rarefactions. So the only way for that cone to move itself forwards and backwards is if it was connected to something that can push or pull it. In this gamma phone that we have over here, we have a needle that's pressed on top of a disc, and the disc has its own grooves. And the grooves force the cone to move forwards and backwards, thus amplifying the sound through the horn. Okay. In fact, inside over here, there's a little piece of plasticky looking thing called a diaphragm. So really the needle is causing the diaphragm to vibrate, and then we have the horn to amplify the compressions and rarefactions generated by the diaphragm. Okay. Now today we don't use this technology, but it's all based upon this. Because if you can cause sound to be generated by moving cone back and forth, why not replace the needle with a solenoid and a permanent magnet? All right, so the solenoid is connected to the cone itself because it's a lot lighter and has a lower inertia with it, so it's able to freely vibrate. And then the heavy magnet is always on the base of the speaker. And here's a short little video explaining how speakers work. Or maybe not. Of course, the next question is, how in the world does a speaker work in the first place? Time for another episode. There are 3 components to a speaker. There's obviously the speaker cone itself, but the only way for it to move back and forth, is by the use of an electromagnet and a permanent magnet. An electromagnet is a wire that's wrapped around in a cone many, many times. If I pass electricity through this electromagnet, it'll end up creating magnetic fields, which will then either fall in love with a magnet or cause a magnet to run really far away. Safety first. So the current flows in a way that it creates a magnetic field that loves the magnet will become drawn in. Now, if I flip the current around, the magnet's going to hate the electromagnet. Oops. So by constantly varying the current back and forth, I can cause a magnet to move back and forth, back and forth. And if I connect it to a cone, I can cause large amounts of air to move back and forth. One day I found a lonely highlighter left on the ground. I decided to adopt it and wrap a couple of wires around it, thus making it into an electromagnet. And if I connect this electromagnet into an amplifier, and I connect the amplifier to a music audio device and I play it, well, for one thing, the sound's not going to be very loud because it's going to only move very small amounts of air. So I have to yet again connect it to a cone. And if I turn it on, I should be able to hear something. Now, of course, I'm not going to hear anything because even though the electromagnet is working, it's not pushing or pulling away from any permanent magnet. So once I incorporate the permanent magnet into this setup, now we get some music. Well, I hope that you enjoyed today's episode. For more adventures like this, make sure you like, click, subscribe, hit that bell button in the corner so that you can receive any updates for any new videos I might make in the future. And until our next adventure, awesome. And that's it for today's lesson. But now that I had a chance to test this equipment one more time and actually put a shunt wire on top, where's the button? There you go. All right. I just want you guys to be able to see this, and this does happen. All right. So once again, I have a current in this setup over here. I just have current that's going towards you on this black wire and returning from you through the white wire directly up above. I know that you can't see it from camera view, but what I did was I short-circuited over there, and maybe I should have demonstrated that afterwards because this was working, and I don't know if it's going to work anymore now, but hey, we're doing it live, and I hope that I didn't damage that. So if all goes well and I push the button, you'll see that these two will repel each other. Sweet. There you have it. Physics at work. There's some smoke there. Now the fuse is popped, and that's it for today. Thank you guys for joining me, and I'll catch you guys in the next episode. Bye for now.